Okay, before we continue to discuss chapter 5, okay, let me highlight on chapter 4. There's a there's a one point that I forget to mention, where actually that is the things that you need to know before before you learn chapter 5. Okay, if you realize in this slide note talking about frequency domain, image enhancement in frequency domain, you realize that most of the image have been drawn uh, not in the matrix or in the typical image representation. Okay, if you talk about typical image representation, normally we form the image in form of matrix. Okay, uh, so but in frequency domain, most of the time you can see that instead of using, of course, like I mentioned in chapter 1, when we talk about image processing, the because it's a two-dimensional signals, then the proper way, or the common way to represent the two-dimensional signal is in matrix, because um, with, that is more meaningful as compared to represent it by using the stem function. Okay, if you remember about stem function, it's something like this. Okay, which is like yep, this one. Okay, you can see this one. Okay, this one. Okay, where you draw that your image in three-dimensional. Okay, in three-dimensional, where you have x, y, and f. Okay, that if you're talking about spatial domain. But when you apply this thing, okay, image processing, most of the time you are not represented in this way. You are represented in matrix, which is easy to see and more meaningful. However, in frequency domain, you will realize that most of the time you are using this kind of representation, uh, because in frequency domain, it's hard for you to see by looking at the typical matrix form. Okay, so that's why you can see in chapter 4, okay, when we talk about the frequency domain, okay, you will realize that when we talk about, for example, I give you example. Okay, last time we talk about our low pass filter, okay, which is this one. See, in this one, okay, this is actually is a stem function representation. Okay, it's a 3D representation of your image. If you draw this image in in metric form, okay, it should look like this. Okay, that is not displayed here. Okay, your image will look like this. So your image should look like this, means that this one is black. Okay, because the pixel here is 0, and you will see this one is white, which is represent this circle. So another, okay, and so that then you need to remind, actually this 3D model, you just assume you assume that if you see this image, actually this is where your IC is. Okay, this is where your IC. Okay, so but if you represent in this way, it's very hard to discuss about the frequency domain. So that's why in this topic, most of the time you will see that in frequency domain, we always generate in 3D form like this. Okay, so if, for example, I think this one, you can also see that this issue in this example there, you can see in this slide, the one that display in metric form or in typical image form is this one. Yep, this one. Okay, so you can see here. How about yeah, this one. So you can see here. Okay, this is your image in spatial domain. If you change it into frequency domain by applying the Fourier transform, this is how it's look like. But of course, you will not. Okay, you will try to question the outputs there. How can this thing, after you convert into Fourier transform, will become like this? So you cannot see this issue. Okay, you cannot see this thing is because because actually this is displayed in typical image representation, which is in matrix. Okay, but if you draw in 3D, then you will realize that there's a reason why if you put this kind of image, then you when you convert into Fourier into frequency domain using Fourier transform, this is how it's look like. I think this one I also discussed in the first chapter, second chapter, but I don't emphasize on this issue. Okay, let's go back to that whiteboard. Okay, this one. Okay, so if you remember about this one, the terminology is here, as you can see. Okay, this one is discussing about this slide. Okay, if you have some sort like image like this, okay, if you plot the one-dimensional signal that cross at the center section here, okay, to make some terminology, if this is in one-dimensional signal version, then this image will look like this, which is your square function or rectangle function. Okay, so if you have this kind of function, if you convert into frequency domain using your Fourier transform, you will produce this kind of wave, which is called sinc function. Okay, this one is standard. I think you can refer to any material related to frequency domain. You will see that any square function like this, okay, if you convert into frequency domain using Fourier transform, you will get this kind of wave or shape where this is called as a sinc function. Okay, so if this one convert into this become sinc function, then if this one is a two-dimensional version of this one, if you convert into Fourier transform, then if you draw the 3D, then it should be a two-dimensional sinc function. So two-dimensional sinc function might be look like this. Okay, you have in that direction and then in these directions. Okay, so you have a 3D sinc function. So if your eyes is looking at this side, then if you plot or if you draw the image in matrix form, then that's why it's look like this. Okay, this one is actually the one which is similar to this one if you draw in 3D version, okay, in three-dimensional model. Okay, but because you draw it in image, that's why it's look like this. In matrix form, that's why it's look like this. So that is that's why this kind of representation in frequency domain it's not so meaningful. It's not so meaningful, and also not so it's not so easy to interpret. So that's why you need to model it by using 3D representation or in stem function. Okay, in two-dimensional stem function.